Hi, I'm Jeff Johnson. I'm from Facebook AI Research. Here today to talk about a lot of the software challenges which are faced in this new area of deep learning and how we use GPUs. Some general misconceptions about the trade-off between GPUs and CPUs. And I'll also go into some of the software work that we've been doing recently at Facebook AI Research. So a large part of this talk will be talking about so-called deep convolutional neural networks. It's very much been a revolution in machine learning, but it's been a long time in coming. Convolution as a basic unit for these networks has, the idea has been around since 1980s. The idea is it provides some form of, translation invariance or actually equivariance in, going over features. And but it really hasn't been used until the 2000s because convolutions are rather computationally intensive. The basic idea behind convolutional neural networks is that we basically want to feed raw data to networks. We want to avoid feature engineering. A lot of the traditional machine learning tricks with SVMs or linear classifiers or other statistical techniques pretty much require that you massage your features and get it in the form that you can then classify on top. The idea of convolutional neural networks is pretty much with enough data, you let the network discover the feature representations. And what's interesting is it's not just for videos and images, which have been a hot topic of research, but it can even work for natural language processing. There's even some results that you don't even need to segment words. You can just feed raw character data in English or Chinese or whatnot to a convolutional neural network, and I actually tease out the details between things. So these convolutional neural networks, they've been around quite a while. At the top, MLconf and who are also part of Facebook AI Research, is a relatively, an example about a decade into convolutional neural nets. This is the structure of LaNet5, which was pretty much used for recognizing handwriting on most of the checks processed in the U.S. It's it has a number of layers, but sort of jumping forward, this is the real revolution, which pretty much made everyone wake up and take notice about convolutional neural networks. Out of the University of Toronto, of course, all three of these people are now at Google. The so-called AlexNet, which was the first big convolutional neural net to be run on GPUs, which pretty much blew every other image recognition and classification technique out of the water. So looking at 2D convolutional nets, there's been a lot of progress over the past couple of years in terms of being able to classify an image, given a picture of a dog or an image or something like that, being able to, in a wide variety of poses, being able to accurately recognize, what it is. Starting from AlexNet in 2002 to some of the more recent 2014, 2015 results, they're pretty much close to human performance in the matters. As you go down to these, more recent networks, the progress is towards very much smaller convolutional kernels and very deep nets. And deep video, which is out of Stanford and Google, which represents a combination of different convolutional techniques together. Convolutional networks are also used in text and NLP. Two examples, one of which by Roland Colbert, who's at Soper Lab, and Jan LeCun, with Xizhen Zhang, I believe, of NYU, a recent paper. This is feeding raw text data to a convolutional neural network and actually having it recognize and understand. Of course, very much in this topic of deep networks, there are more things than just convolutional networks. You have recurrent neural networks and long short-term memory networks. These have many different paths to the network, multiple layers, and there are many dependencies and serial dependencies used to process this sort of stuff. So if you look at what actually what are the things to say about all of these deep neural networks, is that pretty much all of these are trained with supervised learning. We have we have text or we have images. We know what category they should be. Unsupervised learning is very much an unsolved topic. For the most part, they're trained with back propagation, stochastic gradient descent variants, momentum methods, so on and so forth. There's some work on things like target prop and whatnot, which are outside of this. But one thing to note is that we have hundreds or thousands of GPUs or Xeon 5s. We don't really have any idea how to use them. The strong scaling aspect is very much unsolved. Pretty much most of the ways that people use massive numbers of GPUs for these is just by giving the model independent copies of the model to many machines. Like two examples are these distributed parameter space exploration. You pretty much just have machines work on their own and periodically exchange information in like the hog-wild stochastic gradient descent technique. Or you give copies to a bunch of machines and have them work on trying to optimize hyperparameter configurations for how the network is set up. And this Bayesian optimization paper, which is now this company, the technology for this is in this company called WetLab, is very much a technique that a lot of people are playing around with. So if we look at some of the characteristics of actually implementing these deep convolutional neural networks on CPUs and GPUs, what are they? Well, for one thing, deep networks are very much flop eaters. There's a reason why they haven't really been used until recently. Convolutions are very computationally expensive. There are a lot of point-wise calculations which are applied to large sets of data, exponentials, these rectified linear units, point-wise, like multiplications, additions. And we have collections of neighborhood reductions, like we wish to sum little neighborhoods together with a pooling and convolution. A lot of these networks combine these things together. And of course, if you attempt to scale up the size of the network, you're increasing ever more the work that you need. This increases the learning capacity of the network and the ability to network to classify and generalize new things, but you pretty much need that much more, 10 times more data to feed to it. So this is part of the problem of actually attempting to scale up and use many GPUs or CPUs. Another thing as well is that deep nets are very much bandwidth eaters. The more parameters that you have in these networks, this increased learning capacity, that's just that much more memory you have to have resident on the GPU or CPU, and that much more data that you have to exchange if you split them between machines. Some of the techniques that people have come up with to try to reduce the amount of data that you have to exchange are compression and quantization. There's a paper out of Microsoft Research on 1-bit stochastic gradient descent, where actually you attempt to compress down the data that you exchange between machines to just 1 bit per floating point number that you use. And of course, when bandwidth utilization, memory, becomes a problem, idea is you want to reuse more memory while all this information is local. And this will get into kernel fusion, which I'll talk about later. But there are a lot of problems with that, and it's very much sort of like a generalized programming language problem that people deal with. In a lot of ways, these deep networks are very much sensitive to latency. The faster that you can execute each individual layer, the faster you can get through your training set. There's very much serial dependency of training. You have to take many small, mini batches of data and pass it through the network back and forth, back and forth, back and forth, and you can continue until you've actually completed that. There's very much a serial dependency of all these multi-layer networks. You can't execute layer 2 until you've executed layer 1, and so on and so forth. And when you have more complicated networks, which just aren't straightforward, there are many pass-through, and there are many dependencies in the computation that you have to go through. But I would actually say one interesting aspect that a lot of people overlook is that in a lot of ways, deep networks are also very small problems to solve. The idea of a convolutional neural network is that, say for an image, you're taking a large image, say like a 256 by 256 or 512 by 512 image, and you're actually trying to reduce the amount of information that's in that by taking it, expanding it to a larger dimension size through convolution or through linear mapping. We'll form some nonlinear reduction on that and then squeeze it back down. You do this in many different loops. In a lot of ways, these problem sizes that you see are very much tiny relative to what most people have been using GPUs and CPUs for in the high performance computing world. For instance, a lot of times, for oil and gas, things, you have very large FFTs that you have to run. Say weather codes and things like that. You have these massive grids that you have to compute across machines. Whereas for convolutional neural networks, a lot of times you have to deal with things which are data size, say 23 by 23, very irregular sizes. You have lots of them. Those create a lot of boundary effects and problems. You have a lot of sparsity text issues. The data is very sparse. And in a lot of ways, the smaller the data that you process, you kind of get into this regime where the GPU is more hungry for more work, and you can't actually feed it fast enough. The amount of time that it actually takes to give the GPU the work is, can be comparable to the amount of time that it takes to actually compute that. So, sort of looking at the tools that people have to solve these sort of things, vector processors, very much they've been around for a very long time. An early example is the original Cray machine. It's pretty much, hopefully everyone's familiar with it. Given one instruction, operate and do the same thing on multiple pieces of data at the same time. But of course, like I, would actually say that, vector processors and vector instructions, in a lot of ways are actually pretty hard to use, especially if you have to always ensure that you're operating on 4, 8, or 16, or so on and so forth pieces of data at a time. Like it's great for massive problems, the ones that you tend to face in the high performance computing world. But when all of your problem sizes, say maybe, like for like size 18, like you can't really get the machine to sort of like hit its stride because the problem sizes are too small. There's a lot of overhead that you have to do in that, or a lot of ways, like that you have to combine things together. So sort of looking at the GPU side of things, kind of like why are people using GPUs for these things? So really it's kind of a vector machine as well. It's this like variant that Nvidia calls SIMT, single instruction multiple thread. The idea behind this has actually been around for a while. You can take lots of simple cores. This is the original connection machine, which had 65,000 1-bit processors. You can combine with this idea that over time, main memory is only getting slower and slower relative to the processor. Well, one way you can cover that up is just by having massive number of threads available and switch between them, which is something the Terra architecture in the mid-90s explored. In the way that the GPUs became a thing for processing is that this kind of like massively parallel machine came about from the graphics world, that you have all these simple programs that you have to process on each pixel or each pixel, and that became a platform that people started using for general purpose computing. So comparing the general issue of a GPU versus CPU, I'd sort of say they sort of represent like a different form of vector programming, where the basic unit is this like 32 wide vector threads. But I would actually say that sufficiently optimized CPU code is on par with GPU code. The problem is it's just actually pretty hard to get up there, especially with latest extensions to AVX and having to exploit and know about the multi-level caches and prefetching and data layout and all that sort of stuff. You can actually get up to GPU level performance. But in a lot of ways, it's just sort of easier to get that sort of like first 50% of like peak machine performance with GPU than CPU. And the sweet spot, is kind of like different. CPUs, tend to kind of like excel. Well, like excel is maybe a strong word at sparsity and branching and pointer chasing, whereas GPUs, are very much good at stream processing sorts of issues. So like parallelization and vectorization. Given that we have a lot of work, how can we like take advantage of these basic attributes that we have multiple machines and we have vector processors to use it. In a lot of ways, the serial nature of the programming languages that people use on the CPU hide these opportunities. Like auto-vectorizing and parallelizing compilers have been around for a while, but they still can't compete with sort of like hand-rolling, and it takes a lot of time to actually hand-roll these things. Something that's very interesting in the space, and I only hope that it becomes more relevant, is that there are these domain-specific languages where you actually express the operations, like this DSL called Halide, which has come out of like MIT, I believe Google and some other places are using. We at Facebook AI Research have played around with it a little bit. They very much show promise in terms of generating code for vector CPUs or GPUs, but I kind of feel like it needs a few more generations. In a lot of ways, just trying to sprinkle in parallelism by taking existing codes and putting some OpenMP fragments, it really doesn't get you the performance that you need. So sort of comparing the GPU versus CPU issue. This is sort of what I would actually say. Flops-wise, both GPUs and CPUs, have them. Main memory bandwidth, in a lot of ways, I'll get to the point that deep learning algorithms are pretty much bandwidth limited. GPUs win with that, but ZM5, is very much competitive or even past GPUs in those ways. Latency, if your program is very latency sensitive, the CPU would be the better choice. The GPU, caches are pretty much, not something that you can depend upon. Dealing with small data sizes and branches and things like that, they're it's sort of a mixed bag. And very much the parallel programming model, like the GPUs were kind of designed around it, but it's still kind of like hard to use. So given the tool of these vector machines, and given the problem, what's the solution? So looking at 2D convolutional nets, the problem is somewhat computationally expensive. The first layer of AlexNet, is like 13 billion floating point operations, a lot of data to read in and read out. If you were able to sort of like utilize all the data that you read in perfectly, You could get 175 flops per byte that you loaded, but that's of course impossible. If you had to reload all the data in all the time, it's very low. The problem is really that all of these caches are not large enough for perfect reuse. And convolution is becoming a thing. Let's optimize it. The space of all the possible problems is like very large. So like some problem, like a thing that people have done is convert this to a much simpler problem that people have already optimized. And people get their entire PhDs on trying to improve matrix multiplication. Nvidia and Intel have done a lot of work with this. Nvidia has rephrased convolutional matrix multiplication, which is the basis of their Cudian library. But in a lot of ways, like these libraries that people have written, they're very much optimized for large problems. And like the problems that we have, 13, doing a 3x3 convolution on features which are 13x13 or very small, it's really not enough work to feed a GPU. In some ways, even a CPU. This method of converting convolution to matrix multiplication, it becomes kind of like intractable. And these small feature maps and boundary conditions, they're sort of bad for GPUs. You get all this inversion stuff. So to look at some of the work that we've done recently at Facebook AI Research, so we've implemented a convolutional layer which is actually available in open source. It's like available as part of the Torch environment. We have a paper on it that's been accepted for the iClear Compass track, talking about our implementation of FBFFT. And of course, discrete convolution, you can convert it to a pointwise multiplication, the Fourier domain. But the thing is that you can actually kind of choose what size Fourier domain to use for that, and it is much faster to do that. And for 5x5 kernels, it's way faster than Cudian. The basic idea behind FBFFT is that like Nvidia's COFT is optimized for large sizes. We pretty much have like smaller data a lot of times. We have convolutions on 13x13 or 23x23 sizes. Try to fit as much data as possible in registers and focus on the work as a unit of computation. Considering all these problems, data layout becomes a thing. Different implementations of convolutional networks focus on what's actually the innermost feature, which is very important for performance, both on CPUs and GPUs. In a lot of ways, this kind of choice varies. Whether or not you want large mini batch sizes, or you want small sizes. You potentially, with batch size of 1, you can get faster convergence, but there's the latency issue to take into account. And smaller problems, like 1D convolution, you really need to take into account this layout and batching issue. And we've done this with part of our FBconf package to like really exploit data layout and batching to speed up 1D convolution for text. So looking at latency hiding, these sort of issues that you're sort of like one of three things. Are you compute bound? Are you bound by like your memory bandwidth? Or are you bound by just latency? I would actually say that pretty much all deep learning algorithms are bandwidth bound on the GPU. They have very low math intensity. For instance, Nvidia has actually said that SGEM is bandwidth bound, but DGEM is compute bound on the GPU, which brings you this idea of kernel fusion. A lot of ways, how can you reduce the amount of memory that you're consuming? Like by exploiting, like register reuse and the data that you may already have loaded in caches. The sort of problem is that in a lot of ways, fusion becomes an issue on the GPU, but not so much on the CPU. At the lowest level, the CPUs have large caches that you can use, that you can interleave these operations. On the GPU, you have to actually fuse the combinations. So like CUDA kernels is hard boundary. There are other things you can do on the CPU. CUDA sort of has some problems that like make it hard for the optimizer to see past that. And in a scripting language environment where you're plugging modules together, it becomes more of a problem. And so just sort of like running out of time here, but Cradle Fusion, like some of the work that we've been doing recently with transposition in Torch and trying to fuse operations together and get things to work is something we're looking on because we're very much bandwidth bound and wish that fuse as much stuff together as possible on the GPU to really explode the power. Thanks.